So suppose you are staring at an integral like this, and of course first instinct is to try u substitution. So maybe you can try letting u be equal to x. This leads to du equal to dx, but this doesn't solve the problem of e raised to x out here. That fails, you might want to try another. Let's say u equal to e raised to x. This leads to du equal to e raised to x dx, but that doesn't solve the problem of x out here. Obviously, u substitution seems to be not applicable to this problem, so when u substitution stops working, what do? Well, you need a new tool, and that is where this tool called integration by parts come in. So this is what we will be focusing on in this video. So integration by parts is given by this formula out here, given by the integral of u dv equal to uv minus the integral of v du. So essentially, we would like our given, say, example to match this formula so that we can express it of this form. So it is also called the reverse product rule, because if you move this to the other side, so maybe we can put it out here. If you move this to the other side, so this will leave us with uv equal to the integral of u dv plus the integral of v du. This thing kind of looks like the product rule, right? Product rule. But this time it is like on the version of integral. So that is why sometimes integration by parts is called the reverse product rule. And also because mathematically, this is derived using the product rule in derivatives. One more thing to observe here is that if we have this formula, the challenge here is choosing which is u and which is dv when we have a certain example. That's actually the hardest part in integration by parts, because derivatives and integrals is kind of mechanical. The decision making is the hard. Fortunately for us, we have what we call this LIATE, which stands for log. So log is ln x, or log x to some base. Inverse stands for like the inverse trig, such as sine inverse of x, or sometimes written as arcsine of x. We also have the algebraic terms. This involves x squared, usual polynomials. This involves as well radicals such as square root of x, since this can be written as x raised to 1/2, as well as 1 over x. Let's write that better. So 1 over x, since this can be written as x raised to negative. So it's also part of this algebraic expressions. Next is trig. I suppose you know that, sine, cosine, and then exponential, like e raised to x, 2 raised to x, and so on. So this will serve as our guide in choosing which u to be placed out here. Okay, so again, this serves as like a guide on choosing u. So the idea here is that you start from the top and then you move from the bottom. That is, log here is the most likely choice of u. The inverse trig is the second likely choice of u, and so on. And the least likely choice of u is exponential. So log and exponential. Okay, so now that the basics are out of the way, we can now try to solve on our first example out here. The one that we showed to be tough when involved with u substitution. So in here, again, notice that this thing, it kind of looks like this. So this is a straightforward application of integration by parts, but we need to decide which is u and which is gonna be the dv. So first, notice that this expression is a product of an algebraic term and an exponential term. Algebraic for x, exponential for e raised to x. So by this thing, by LIATE, our choice of u must be x, because algebraic is higher in the LIATE order. So we will do just that. So let's see. So we let u be equal to x. So if u is equal to x, du will be equal to dx. Okay, I think I'm getting ahead of myself. Let's disregard this first. So this is u, and then dv will be e raised to x dx. So if we do it this way, then this thing perfectly matches this thing. Now in the formula, observe that we have v and we have du. So from here, what we will do is we will differentiate this to obtain du and anti-differentiate this or integrate this to get v. So in a way, you can kind of grasp that the choice for making this LIATE or making this the order is because we want u to be something that we can easily differentiate, and we want dv to be something that somehow we can easily anti-differentiate or integrate. So doing just that, if u is equal to x, then du must be equal to dx. Then v this time, if we anti-differentiate this, e raised to x dx is simply e raised to x. So once we have this, then by the IBP formula, this thing becomes first is uv, so that is this is u, and then this is v minus the integral of v is e raised to x du is equal to dx. There. Then from here, observe that this one is pretty easy to anti-differentiate. We actually did it when we obtained the v. So just recall that out here, that the integral of, so let's write this e raised to x minus the integral of e raised to x dx is simply just e raised to x, and then of course don't forget the plus c, since this is an antiderivative. So that is actually the answer. If you want to simplify it, you can also write it as e raised to x times x minus 1 plus c. So this is the answer for this problem. So it's pretty nice. Earlier, we had a hard time discovering how to solve it, but through this new tool, we were able to solve it. Okay, good. So let's move on to the next one. So this time, we have the integral of ln of x, antiderivative of ln of x. And so how do we solve this? Well, sometimes this is like called the invisible trick or invisible product, since usually integration by parts is applied when we have a product, but this time it seems that we don't have a product. Well, take note that the key here is to just note that okay, let me use green. Take note that we can actually write this as ln of x times 1 dx. So technically you don't need to do that, but it highlights that if something is missing here, if we don't have a product, we can make 1 by just adding times 1 out here. So once we have this, again, like earlier, we inspect. So this time our product is logarithmic times algebraic. 1 is algebraic because you can always view 1 as x raised to 0. Okay, so that's just about it. Checking the LIATE, obviously logarithmic is higher than algebraic. Log is here, algebraic is here. Which means our choice of u, so we let our choice of u must be equal to ln of x, then dv must be the remaining. It will be 1 times dx or just dx. From here, du must be equal to dx over x. So it's basically 1 over x times dx. And then v, since you're just integrating like a constant 1, so this will just become x. Good. So I hope you were able to follow that one. From here, we can now apply the integration by parts formula. So by the formula, this tells us that this integral must be equal to uv. So uv, so we can write it as v. And then, oops, this must be x. Apologies for that. Okay, there. Ln of x. So I just rearranged their position so it would look nicer. But this is u, this is v. So we have uv minus the integral of v du. So v du, we will have x times dx over x. There. Whew. V uv minus v. Yeah, that's it. So that is correct. And then from here, notice that since we have x's here, this one will cancel out. And so we will just be left with x ln x minus the integral of dx. Let's fix this one. Yeah. And then this one is easy to integrate. Actually, we have done it again earlier when we obtained v out here. So this one just becomes x ln of x minus what you call this, x plus c. So that is the answer for this problem. If you want to simplify, you can write this as maybe here you can write this as factor out dx times ln of x minus 1 plus, yeah, I think this one is correct. Yeah, so that is the answer for this problem. So again, don't forget this trick. This is like called the invisible product. This usually applies when we have ln x or maybe inverse. Also notice that usually we don't really have a formula for the antiderivative or the integral of ln x. But through this process, we were able to obtain one, which is this. So yeah. So last example for this video. So we just went over the basic examples for this one. So this time we have the integral of x sine 2x. So clearly we have a product here. So let's determine which u to choose. So here we have a product of algebraic times trigonometric. Check the LIATE table, or just check here the LIATE. Algebraic is higher than trig. So apologies for that noise, but let's keep this going. So given that by LIATE we choose u to be equal to x, dv to be equal to sine of 2x dx. Again, since x is algebraic, it's higher in the hierarchy. Then, as usual, we get du and du and v. So we have here du equal to dx, and then from here v here is equal to, so here is where a common mistake arrives. Usually a student would just say it's negative cosine 2x, since antiderivative of sine is negative cosine. but you're forgetting about 2x out here. So usually when you integrate this, you usually apply u-substitution out there. But once you're used to it, you can simply add the corresponding constant that is missing out here, which is 1/2. Let's see, 1/2. So how was I able to easily determine that? A trick here is just, so you can disregard this first, and then from there you just try to like differentiate this from, by applying the chain rule. Naturally you will need to add this constant 1/2 to ensure that you get this derivative. Okay, so that's just like kind of pro trick, but yeah. So this is a common error, that's why I included this example. Common error here is forgetting this one. Okay, so given that, we can now obtain and apply IBP out here. So by IBP, this one will be equal to UV. So that is equal to, so let's write it as like this. So this is the UV, then minus V du. So minus the integral of V is this, cosine 2x, and then du is dx, V du. Then let's just simplify things. Simplifying, we'll obtain negative x over 2 cosine of 2x plus, plus 1/2 integral of cosine 2x dx. So basically I combined the negatives here and just factored out the constant in the integral. Then here, obtaining the integral of this, again, technically you apply u-substitution, but once you have plenty of experiences, we'll just obtain the following. So let me copy this first. Plus 1/2. So the integral of cosine 2x is just simply 1/2 of sine 2x. And yeah, there. So you can simplify this if you want, but I think I'm lacking space out here, so I will leave it as it is. But basically, again, to obtain this, the trick is similar to how we obtained this. Get sine 2x first, determine which constant you should add, or apply u-substitution if you're not confident with it. Yeah, and so those are our examples for this video. Again, we went over this example, this one, the invisible product, and this one that involves a certain constant trick. Most students usually forget. So just to recap, again, LIATE tells you which u to use in this integration by parts formula. So that's basically the two things you need to remember out here. And although we just went over the basic examples here, it could actually happen that you will be applying integration by parts 3 times in a row or even more. So that happens because, of course, when you apply IBP, you get another integral. And there might be the case that you need to apply IBP again here. There's a trick to solving it, and that's what we will be tackling probably in the next video if you prefer that. Yeah, so yeah, that's about it. Don't forget to like and subscribe on my channel. Don't forget to like this video. Yeah, so that's it. Have a nice day.